Okay, so we're going to do problem 32 on page 654. This will be the last one. This one reads, the permanent electric dipole moment of the water molecule H2O is 6.2 times 10 to the minus 30th coulomb meters. What is the maximum possible torque on a water molecule in a 5 times 10 to the 8th newtons per coulomb electric field? Okay, so let's talk about, first of all, this water molecule. Why is this so special? If you remember back from chemistry, you've got an oxygen molecule in the middle, 2 hydrogen molecules off to the side, and then oxygen also has its own electrons, but since it has 6, it wants to share those other 2 with hydrogen, but really it doesn't want to share them. It wants hydrogen's electrons too. So what you notice is that if you were to look at a probability distribution of electron function, position functions, the electrons would be a little bit closer to the oxygen molecule than the hydrogen molecule. And what this means is that overall, the oxygen molecule has much more of a negative charge, and down here by the hydrogens, there's much more of a positive charge. So a water molecule has an electric dipole moment, okay, because there is a charge separated by a distance. Okay, now when you put a dipole moment into an electric field, so here's our dipole moment. What happens is that electric field is going to be causing a force on these charges, right? So we're going to have, I'll put it in green here, force on the positive one is going to push this way, and on the negative it's going to push this way. And this force has 2 different components. There's going to be a component that's parallel to the dipole moment and a force that's perpendicular to the dipole moment. Likewise down here. Okay, so part of this is going to be parallel, part of it's going to be perpendicular, and that perpendicular force, it turns out, makes the dipole moment want to rotate, so it's applying a torque. If you remember back from last semester, we can define torque as the moment arm length times the force applied times the angle between the moment arm and the applied force. Now, our book also tells us that this happens to be equal to the electric dipole moment times the electric field times sine theta. And you're going, well, how did they get that? Well, if we think about it, the dipole moment is Q times the distance, and then we have our little equation that force equals charge times electric field, so that means the electric field has to be force divided by charge, sine theta. Well, this charge is going to cancel with that, which leaves us with the distance times the force times sine theta. And, well, that looks awfully similar. R is a distance, and then the force is the same. So, in this case, we want to know what the maximum torque is. And the maximum torque is going to occur when the sine of theta is equal to 1, or we could say or theta is equal to pi over 2. Either way, that means Tmax occurs when we have just RF, or just the electric dipole moment times the electrical field. So we have those values. We know that the dipole moment is 6.2 times 10 to the minus 30 coulomb meters, and our electric field is 5 times 10 to the 8th newtons per coulomb. This gives us a maximum torque value of 3.1 times 10 to the minus 21 Newton meters.